All right. How's everybody doing? Are we all having a wonderful and magical day? We're all excited to be here. I know I'm excited. Yay. I assume this meme is foreign because it's American. The only thing you can do when you're 18 is die. Smoke. Isn't smoking 18? No, that one went up too? Yeah, it changed to like 6%. No, I wasn't paying attention. All right. Beautiful. What the hell? All right. You can go off to war and die if you want to. Oh yeah, they'll let you do that. It's a free country. Right on that. That's how a lot of people pay for the college. So today, we're not doing a review because the review absolutely would have just been a bunch of fractions, and everything we're doing today deals with fractions. So we're gonna do enough fractions. I think we can skip going over that stuff again. But we will deal with the concept of ratios, which literally is just fractions. The ratio of one thing to another thing, being able to process that a fraction is referring to something. Unit rates and proportions. So basically applications. We're going to do applications of this stuff. So a ratio is just a comparison between two numbers. They're commonly written in a word form, 2, and then the word 2, 3, that's an option. Write them with a colon in between or as a fraction. And I always say this every time I teach the class, I don't like the first two just because when I think of those, I think of like betting odds. And if I'm doing odds, that would mean something entirely different. So I usually just go with fractions. Otherwise, yeah, it's literally just a comparison between two numbers. So our example here talks about how many players are on the soccer team and the amount of people in each position. And asks what's the ratio of midfielders to the number of players the team can have. So the answer would be midfielders over total players. So 5 to 11 in whatever way you want to write that. With a colon in between, as a fraction, with the word 2 in between, whatever. It's a ratio. We like it. I have no specific problems for this. Literally just the vocab of understanding what a ratio is. Always here. Like email and be like, yo, we missed you. Tell me why you weren't here. Minute rates. I refuse to take this out of any slide. I have literally used this in every slideshow of every class I've ever taught. Welcome to the party. We've got a sign-in sheet up front if you don't mind doing that. I always have this screen grab from an episode of Star Trek on there because it just cracks me up. Because I did fall asleep reading a particularly erotic chapter in my grandmother's journal. First of all, what the hell? Second of all, what the hell? Doesn't make any sense to me. I'm not okay with it. That same episode, she sleeps with the two ghosts that her grandma slept with, or slept with. So that was weird. So yeah, I'm gonna have that slide in there every time, just because that cracks me up. So unit rates. Okay, so we know what a ratio is. A ratio is a comparison of one thing to another thing. You can also refer to it as a rate. Rate of one thing over an amount of another thing. But a unit rate compares an amount of one thing to a single amount of another thing. Yeah, we use miles per hour pretty regularly. Talking about how much mileage you get, it's miles per gallon. It's never miles per 5 gallons. That'd be weird. But yeah, example, if a tub is filling at a rate of 10 gallons every 2 minutes, the unit rate would be 5 gallons every minute, right? And that's a unit rate. It's useful because it gives you kind of like a base amount. If something is like if this tub or anything is filling at 5 gallons per minute, and you're like, okay, well, what if it was like 50 gallons? How long is that going to be? Well, you just divide them and get your answer, right? So that's the usefulness of those. Those we actually got problems. Look at all those beautiful problems. I know you're excited. Calm down. So a car travels 420 miles on 15 gallons of gas, expresses as a unit rate in miles per gallon. So 420 miles on 15 gallons of gas. Hopefully you're not cutting it that close and just running out and saying, yep, that was that many miles. So if you're looking for miles per gallon, think of it as, well, first of all, wrapping your head around it. That's however many miles you travel for every 1 gallon, right? So one thing I like to do is I like to just put my units as fractions. Miles over gallons, miles per gallon, right? And if I use this kind of like a template, I think, okay, well, to find miles per gallon, I could do miles divided by gallons. 420 miles over 15 gallons. And the units would be the same. So when I divide them, I would just get miles per gallon. Remember what that is? So that breaks down to 28. That's miles per gallon, mpg, whatever. That works, right? So if you have your mileage, you're like, okay, I have to go this far. How much gas am I going to need? From that point, you can compute based on the price of gas, how much things are going to cost you. Speaking of costs, a spice company offers different prices depending on how many ounces of each spice a customer buys. Which of the following is the most affordable spice to buy per ounce? So each of these, we kind of have different amounts, right? We have the amount of ounces and the cost. And you're looking for the cost per ounce, right? So if we're looking for the cost per ounce, that means we're going to end up dividing the cost by the ounce. So what I usually do for this problem is because there is so much, I usually just kind of go down the line and write the dollar amounts next to the ounces. So if we're looking for the cost per ounce, then that would be the cost being divided by the ounces. So what we can do Kind of got like a really awful looking chart going here. But we can actually just do this column divided by this column, throw it over here, and we got our cost per every ounce. And we just throw each one of these at the calculator. Well, for the record, I am rounding because some of these will just keep repeating. All right, well, these are all our different options. Which one's the better purchase? Gonna be this last one, right? Because that one has the smallest amount. This one is 12.5 cents per ounce, 11 and 11 and change per ounce, 9 and change per ounce, 10 and change per ounce. This one's 9 cents per ounce, exactly. And if that throws you off a little bit, you could always just fill in that extra zero just to line it up with all the rest. But based on that, that is the smallest cost, so that would have to be our option, right? That makes sense? All right, we're all happy to be here. Cool. Me too. Grocery stores having a sale on crackers. Customer could buy 3 boxes of crackers for $5. Using this rate, what would 5 boxes of crackers cost? If this person is not going to buy that extra 6 box, they're going to be annoying about it. If you've ever worked in retail, we're used to them. So if we're doing this, you kind of think, okay, well, how am I going to go about this? If I'm trying to figure out what 5 boxes cost, I want to know what the cost is per box so I can, multiply it by 5, right? So that's how I'm going to look at it. I'm going to write it down as cost divided by box. So if I know 3 boxes is $5, I can actually work with that. So if 3 boxes is $5, we just need to know how many 5 boxes is. No idea. Actually, when we get to proportions, this would have been easier as one of those. So the cost per box, we can just do the cost divided by boxes. That'll get you about $1.67 per box. And then you just multiply it by 5 again. $8.33 if we don't actually round off that $1.67. If you do, you could get $8.35. So this is without a rounding problem, and this is with a rounding. So another thing you could do is you could very well just take your original amount and before even doing the division, you multiply that by 5, because we know that that's going to be the cost per box. Then you have 25 divided by 3, and that's where you would get this 8.33 here. that's where we would get that 833. If we do round it right here, then that's where we could be off by 2 cents. So chances are any company that's trying to make money off of people is going to be rounding it right here. Then they could squeeze 2 extra cents out of everybody. Any confusion? Everyone properly dead inside? I know I am. This one says a woman flips a coin 70 times and counts how many times the coin lands on heads. Turns out to be 38 times. What is the ratio of the coin landing on heads to the total number of flips? Simplify the ratio. So that's pretty easy, right? Once you get the idea of a ratio, it's literally just write it as a fraction. And if you're saying, oh, 38 out of 70, you're literally just writing 38 divided by 70 as a fraction and then breaking it down a little bit, which doesn't really break down a whole lot, right? Both the top and bottom are even numbers, so we can at least divide everything by 2. 2 goes in there 19 times and 2 goes in there 35 times. 35 is 5 times 7. 19 has none of those, so we are done there. That one's not too bad, yeah? Right, the given rate is a simplified fraction, 4 restrooms for 36 employees. You could write that a couple of different ways. You could write employees to restrooms or restrooms to employees. It doesn't really specify, right? That's where some of the weird stuff comes up when you start playing with just the applications of fractions, because it'll look simple enough, but these 2 options would mean completely different things. How many employees per restroom? How many restrooms do you have to each employee? Well, this one's going to be a tiny little fraction, right? Because there's only so many. But since we have 36 employees and 4 restrooms, it would make more sense to say how many employees per restroom, right? So sometimes you kind of gotta look at what the problem is and think about what the best way to approach it is. Because you absolutely could compute how many gallons you use on every mile. But how useful is that? Can be useful if you know how many miles you're going, right? But that's when you're planning a trip. Most of the time, miles per gallon would work better. But you can invert these ratios, flip them upside down and view them the other direction. It's always this per this. So if you flip it upside down, it's going to be a little bit different. The number 6 doesn't really change things up at all. It's pretty much like that, like the cracker problem, like the ounces problem. You're literally just finding out how much each pound costs, right? So you do money per pound. We could do this without actually writing anything down. It says there's a 3-pound can that costs $8.42. We take $8.42 and divide it by 3. 2.8066666 repeating forever. Okay, we'll keep that in mind. Then the other one is 590 for 2 pounds. 5.9 divided by 2. 2.95. What's the better buy? Well, the smaller amount was the 2.80 and change. So that would be the 3-pound can, right? So that's pretty much the usefulness of unit prices. You can find what's cheaper for you. You can actually find things that are more efficient. or you can just find rates for just about anything. The physics teacher that drove it into my head to keep units on every single problem and every single step. And if you mess up, you can get some really weird options. Doesn't mean they're wrong, you just get weird stuff. You ever see acceleration referred to as meters per second squared? You think, how do you have a squared second? Because it's meters per second. It's the change in the speed over time. Okay. So now we got proportions. So proportions aren't too bad. They're just two ratios set equal to each other, right? If something scales up at the same rate, we say it's proportional, right? So the comparisons of the lengths of a shadow of a small object versus the shadow of a larger object, those would be proportional, right? You actually use that pretty regularly for being able to judge heights or distances that you're not able to measure directly. You find the comparison of something that's going to work out well and you use a proportion. So we generally use cross multiplication to solve these. The example here is if a factory can manufacture 84 bicycles per day when it's at 70% capacity, how many bicycles can be produced at 100% capacity? You just kind of set up your units, kind of like we were doing with the unit rates. You find a good way to write it, like bicycles over capacity, for instance. And that's what we have here, 84 over 70. And we have that equal to, we don't know how many bicycles, so B over 100. So something like that, you would just cross multiply and solve for the B. Then you get your answer. Do you like it? Do we hate it? Let's do a bunch of them. You guys ready to do a bunch of them? Yeah, you guys are ready for everything. Got that excitement to take on the world. For one, we have an 8-foot lamppost casting a shadow 12 feet long. A nearby building is casting a shadow 30 feet long. What is the height of the building? This is one of those situations where it's like, okay, we can measure the shadow, we can measure the lamppost, but we're probably not going to grab a tape measure and start climbing a wall, right? So you set things up as a proportion. Usually I will do, in a case like this, I might do height over shadow. And I always write out my units, whether it's helpful or not. I always do that just so I know that I'm keeping everything straight. Because if you don't keep it straight, if you do height over shadow is equal to shadow over height, the world's going to blow up. Or at the very least, you're going to get marked in, right? So height of lamppost is 8 feet. Its shadow is 12 feet. Is that equal to the height of the building is, I don't know. Let's call it a B. B for building, right? Good enough. And the length of its shadow is 30. Now, at this point, normally we do cross multiplication, right? Because we have a fraction set equal to another fraction. We did cross multiplication last time? I don't remember. Let's just assume. Yeah. So normally you would just do cross multiplication, but if you can reduce a little bit right now, go for it. That'll make your life a little easier. So we can actually reduce this a little bit because both of these are divisible by 4. So 4 goes into here twice, and 4 goes into here 3 times. Now we got smaller numbers we can deal with, right? So if I did cross multiplication, this multiplied onto that, 30 times 2 gives us 60. And then this multiplied onto that gives us 3b. Cool. Effort. We divide off the 3, get the b alone, we get 20. And since this is a word problem, we need at least our units on there. Everything's in feet, so 20 feet. Are we understanding? Am I talking too quick? Am I talking too slow? See if we can get the end of the couple hundred pages of slideshows by the end of the class today. See how far we can do. How far we can make it. My problem with this particular subject is I always expect the pile of slides to last a little longer, and it never does. Number 2, Theo wants to use a cookie recipe that makes 36 cookies, but he wants to reduce the number of cookies to 24. The recipe specifies using 2 cups of sugar. How much sugar should you use? Okay. Get that over here. So we have 36 cookies, use 24, or no, 2 cups of sugar. 4 cookies uses, I don't know, cups. Yes, this is how I normally set up my own proportions. Because we have an unknown right here, so we know that's where our variable is going to be, right? Now the question is, does it matter? Like going back to this one, would it have mattered if I had the shadow over the height? Would that have given us a difference? And in that case, when it comes to setting up proportions, it doesn't. It doesn't actually make any difference at all. Because of cross multiplication, the same 2 items are going to be multiplied together no matter what. So it doesn't matter if we do cookie over cup or cup over cookie. Now, personally, I like the idea of cookie over cup just because, well, might reduce easier just looking at it, you know? So that's how I'm going to work it. So we'll have 36 cookies over 2 cups. Over, or next to 24 cookies over, I don't know how many cups. Let's just slap an X on there. Universal symbol for I don't know. Well, we can reduce, right? 2 goes into this 18 times and into this once. So when I do the cross multiplication, I just get 18x is equal to 1 times 24. I like it. Effort, right? Do your division. We get x is equal to, now you can slap it in a calculator, you can reduce it. Personally, if I was to reduce this as a fraction, 6 goes in there 4 times, 6 goes in there 3 times. So I could either call it 4/3, or I could go with a fraction. You know, this one, honestly, you're playing around with measurement, right? This would probably be the best example for using a mixed fraction. 3 goes into 4 once, and you'd have 1 remaining. So 1 1/3 cups. That would probably work better because it was the last time you had a measuring cup that said 4/3 of a cup. You actually might have, I don't know. but it works. One says, in order to determine her pulse rate, June's nurse counted 18 beats in her pulse in 15 seconds. At this rate, how many beats would she have per minute? Now, yes, I do know that there's an easier way to do this one. Beats. Okay. But the usefulness of this is playing around with the units. Because you're looking for beats per minute. So if we have 18 beats for every 15 seconds, you don't know how many beats are going to be in, and you can't say 1 minute, you have to keep your units correct, right? All the other ones, we have unit over unit equals unit over unit, and they're all the same setup, right? We absolutely cannot have this as 1 minute. If I did, we have to convert that. So that converts to 60 seconds, right? We have to convert it to be the same units that we're using on the other one. Otherwise, the world blows up. Don't blow up the world. Not a big fan. So if I set this up as beats over seconds, 18 over 15 equal to X over 60. Now, I said this isn't the proper way to do it. Best way to do it would be multiplied by 4, right? Because 15 seconds goes into a minute 4 times. So on something like that, you would probably do it that way. And if you could see that that's going to happen, if you can see that something's going to break down really nicely, we can get away with not doing cross multiplication. Like on this particular problem, I might just look at it as multiplying 60 onto both sides. That'll cancel out this, but that'll let me reduce the 60 with this 15. So instead of cross multiplication, we're just multiplying off the 60 and reducing. At that point, there's our 4 times 18. That's what, 40, 72. So, you know, that's a pulse. Not awful, nowhere near mine. Will it work for everybody? Are we all happy? Yeah, we're happy. But yeah, if you didn't recognize that that was going to happen, you absolutely could have reduced here and done cross multiplication. You could have not reduced, just started off with cross multiplication. You would have gotten a big number, right? And 80 divided by 15. That's awkward math, but it would work. So there's a bunch of different ways to do these types of problems. Once you do, you know, 1,500 math problems, sometimes you can take a look at something and be like, I can just multiply off the 60. That'll work. Okay. How are we liking proportions? Is anyone horribly confused? No one's freaking out. I'm gonna jump to the last one and then we're gonna move on to the next subject. Sound good? Cool. This one is absolutely a dig at my old roommate. Micah can eat 21 hot dogs in 15 minutes, and I would believe that. Micah can eat 21 hot dogs in 15 minutes. He wants to know how many minutes it would take to eat 35 hot dogs. If she could keep up the same pace. I think I've tried to do in previous classes that never caught on, and I tried to be like, okay, give me names of people that you've hated throughout your life and I'll make horrible word problems about them. I don't know why that didn't catch on. I feel like that would have been more fun. I'll make problems about somebody eating the heads off of sea bass. I don't care. It'll happen. I don't know. Okay, so we got 21 hot dogs for 15 minutes. 2 hot dogs over minutes. Always concerned when I hear about a hot dog eating contest. Okay, cool. I mean, I know I'm unhealthy. Somebody decides that they want a record for being unhealthy. That's your own damn problem. 21 hot dogs, 15 minutes. That would equal to 35 hot dogs over heck if I know minutes. So we could reduce this fraction right here. That'll make our lives easier. 3 goes into here 5 times, and 3 goes into here 7 times. Cool. 7/5 is better than 21/15. A little easier. Cross multiply. 7 times x is going to be 7x, believe it or not. Then 5 times 35, that 175. Right off that 7. Okay, x is 25. That was in minutes. I get an email about class. All right, well, that's a good reason. They used that like an hour ago. All right. Cool. All right, 45 minutes in. That's really everything I wanted to cover today. So let's keep going. Let's look at other stuff. Isn't that a great idea? Yeah. Good thing I over prepared. Way too much. We'll just stay here till tomorrow. Let's just keep going. Guess what? Do like 12 hours of math? No? Come on, I got tomorrow off. We could do this. It'll be fun. Okay. Let's do some prime factorization. Just jumping into factors. Best thing about this, easy as hell. So, factoring is the process of breaking down a number or expression into its smaller factors. Factors being numbers that you can multiply together to get another number. Okay, cool. I actually do have an explanation on where prime number is. Like, why am I going into all this? And like, I'm not even covering prime. So you break something down, you chop something into multiple pieces. You're like, okay, cool. Those are now factors. So prime factorization is literally breaking down a number until you can't break it down anymore. So you get two pieces of vocab. You get prime numbers and composite numbers. So prime numbers are whole numbers larger than 1 that can't be made by multiplying other whole numbers. It's divisible by only 1 and itself. So there are things you can't split up. Composite number is just the other ones. Composite means it's made up of more than one thing, right? So it's further divisible. Also, I love that comment. Oh, honey, look at all these poor orphans. We'll take them right. Oh, Stuart Little. How would you go to an orphanage and find a pet? Much of the next couple of slides I'm going to be skipping. So if you're doing a prime factoring, you might take a 12 and start dividing. So you might say, okay, 12, what goes into 12? I don't know, 2. Okay, so you get 2 times 6. Okay, 2 is prime, 6 isn't. So you break it down further. 6 breaks down to a 2 times 3, right? Neither one of those can be broken down further. So you can say, okay, 12 is 2 times 2 times 3. Blah, 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 blah. Blah, blah, blah. Okay, I like this better. This is what I'm going to do every time. So factor trees. Now, the funny thing is I skip over all that. I blah, blah, blah. I was the one who wrote it. It's not useful. Why do I have it? I don't know. Why did I do that? So, a factor tree. Factor trees make lives easier when it comes to breaking down numbers because you literally just start with a number, put 2 lines below for just separate branches and say, okay, what breaks into 48, for instance? 2 times 24. Okay, cool. If 2 is prime, you're not going to branch that one off. 24 is obviously not prime, you can branch that off. It's 2 times 12. 12 is 2 times 6. 6 is 2 times 3. Cool. Once you get down to the bottom, once everything is broken down, all of those prime factors are going to be your prime factorization. Those are what goes into it. And it doesn't matter how you break a number down. You are always going to end up with the same prime factors for any given number. Now, because of that, as an example, I wrote off to the left, well, if I had 48 and I decided to break it down into 8 and 6 first, well, 8 is 4 times 2. That 4 is 2 times 2. So the 8 is 3 2s. 6 is 2 times 3. Okay, so we had 3 2s, another 2, and a 3. That's exactly what came out of the tree on the right. So it doesn't matter what you split and which direction, it's always going to break down the same. So it doesn't matter how you write it. Okay. So, yeah, that cracked me up. Boy, did her Everclear and Everclear grain alcohol and just grilled beef. Delicious. These all go pretty quick. For instance, 100. 100, you could go a bunch of different ways. You might say, oh, it's 10 times 10. You also might say, oh, it's 2 times 50. Doesn't matter what you start with. Let's say I did 10 times 10. Okay, both of these break down further. 10 is 2 times 5. That one is also 2 times 5. So when it comes to writing our prime factorization, I recommend writing them all in order. 2 times 2 times 5 times 5. I usually work my way out. Kind of makes your life easier to do it that way. Now, one thing that I've kind of started doing is that if I have a factor tree and it's big and it's huge and it goes in every direction and there's stuff everywhere and it's a horrible mess, once I break something down, a lot of times I'm just gonna cross it off. That way the numbers that are left are the ones that I'm actually caring about. Once that 10 turns into a 2 and a 5, I don't care about it anymore. It's not there anymore, it's 2 and a 5. Okay. Let's kill all those. Effort. Let's skip number 2, go straight to 3. 3 is 144. 44, we got 2 times 72, which is 2 times 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. Cool. We could see that that works that way. Another way you could have done this would have been to say, oh, well, I recognize that's the perfect square of 12. And you could have broken those down from there. Oh, this is 6 times 2, which is 2 times 3. Or I could have broken 12 down into 3 times 4. 4 being 2 times 2. And then you can see the, well, this is easy to tell exactly what I have, but this is a horrible mess. So horrible messes, I cross off what I've broken down. That way I can see, oh yeah, 1, 2, 3, 4 2s and 2 3s. Yep, that's exactly what I got over here. Pile of 2s, couple of 3s. How do we feel? Is that doable? Cool. Let's see, do I have anything particularly difficult? No? That's not fun. Let's make something horrible. Ooh, that's a big number. Got enough room for that? Let's see what happens. Okay, here's a horrible example. It's all well and good when it's like 3 digits. What the hell are we gonna do? You know what? What are we gonna do when we have 38, 846? Now let's make that worse. Either way, there we go. 38 million. Let's factor 38 million. Isn't that horrible? Why the hell would I do that? If you do this one, you can do all of them. Problem solved, right? And all you really need from a problem like this is strategy. You need to be able to think, okay, how do I approach this? What is math class good for? It's problem solving skills and logic. That's, you get those concepts down and you can pull off all the math with enough time. You just need your problem solving skills and logic. I see a problem like this, I think, oh, I gotta do a prime factorization. My first thought, it's even. If it's even, it's at least divisible by 2, right? So if I divide that by 2, I get 1942340 That's big, right? So, okay, I might start thinking, okay, maybe I want to divide this, maybe I want to try something bigger than 2, right? I might try 4, I might try 8, might try something with a bunch of 2s, right? Made up of a bunch of 2s. So if I divide it by 8, I get something with a decimal, which means it didn't work. So if I go back and I divide it by 4, I get something that didn't have a decimal, which means this is divisible by 4. So I get this ugly mess of number. Okay. And while it may be an ugly mess of number, the thing that stands out to me is that it's not even, right? So once I get to a point where there's not an even number, I know that no, I will not be able to divide this by any even numbers ever again. It's not divisible by 2, 4, 6, 8, 10, 12, 150, whatever. It's not divisible by any of those because every even number is divisible by 2. It ends in a 1, it's not divisible by 2. Okay, so then we might move on. We might think, let's try 3. And in fact, this number is huge. Maybe let's try a bunch of 3s. 3 times 3 times 3 is 27. Let's see if it's divisible by 27. Nope, I get a decimal. My decimal has a third, so I think I'm on the right track. Let's try dividing by 9, and it goes in even. That's a weird number. 539, 539. Oh, I was about to make a horrible mistake. That 4 breaks down to 2 times 2. You can tell this problem is going to be a horrible mess, so I'm just going to think crossing things out. Okay, well, the 9's easy. 3 times 3. The hell is up with this thing? Well, I tried dividing by 27 and it didn't work, so I know this isn't divisible by 3. It doesn't end in a 5 or a 0, so it's not divisible by 5. Next even number might be 7. I divide it by 7, and I get 77077. You get some weird sequence like that, chances are this thing's going to be divisible by an 11 in there. I'm not even sure what it is. I honestly just took a bunch of prime numbers and multiplied them together and wrote down the result. So I don't remember. Okay. Well, what I usually do, instead of jumping to the 11, a good strategy to have is just exhaust your factors. I know that a 7 went into that. Does a 7 keep going into that? Divided by 7? It does. Divided by 7. Oh, okay. It'll go in 2 more times. So I can actually divide this by 49. I get 1573. That's 7 times 7. All right, well, 1573. I've done 2, 3. I know 5 can't go in. 7, 9 won't work. Felt pretty good about that 11, right? Try 11, 143. Is that divisible by 11? It is. That's 11 times 13. Okay, can't break those down any further. So what the hell did I just do? 1, 2, 3 2s. 2 3s. 3 7s. Let's start that over here. Cough. 2 11s. And a 13. So got this nice horrible mess of numbers. Isn't that beautiful? So if that makes sense to you at all, you could break down any number. All the numbers. All of them at once. Isn't that hideous? Are we happy with that? Are we further dead inside? Nobody's screaming on the outside yet. That's a good sign. Well, we got time for one of everyone's least favorite things. We got greatest common factor, which will lead into least common multiple. Greatest common factor is easier, least common multiple always causes problems when I cover it. So greatest common factor, why did we just do a bunch of factor trees? Why did I remind people what factoring is? So greatest common factor is a fundamental concept in math representing the largest number that can evenly divide two or more given integers without leaving a remainder. Literally just, it's the biggest thing that can go into a bunch of different numbers, right? Now, how would you find that? Well, conveniently enough, you break things down into all of their factors, so factor tree. All of the factors that they all have in common would multiply out to be the greatest common factor. Write down all the prime factors for each number. Look for the numbers that appear in the factors of all the given numbers and multiply the common prime factors together. So you literally just do it with a factor tree. So if you had 24 and 36, you break them both down. 24 gives you 2 times 2 times 2 times 3. 36 gives you 2 times 2 times 3 times 3. Okay. What I usually do at this point is I say anything that's common to all of your numbers, you circle. So I would have circled a 2 out of each one, then another 2 out of each one, then a 3 out of each one, right? That's what they all have in common, is at least 2 2s and a 3. You multiply those together and you get 12. That's the greatest common factor. That makes sense. 12 is the biggest thing that goes into 24 and 36, right? Makes sense. So let's do a bunch. Greatest common factor, 15, 30, and 105. I'm going to write them down, kind of separate it out. Then I'm just going to drop the factor trees directly below them. So 15, well, that's 3 times 5, right? 30, 3 times 10, 10 being 2 times 5. And 105, well, it's divisible by 5, right? 5 actually goes in 21 times. 21 breaks down to 3 times 7. So the idea is, if something is common to all of them, like this 3 is in all of them, just going to go through and circle a 3 out of each one. There's a 5 common to each one. So our GCF, 3 times 5, 15. Makes sense. 15 goes into those, so it'd be your greatest common factor. It's perfectly fine for that to be one of your numbers. Sometimes the whole thing goes in evenly, you know? Let's do number 3. is 24, 168. Break them down however you want to, doesn't really matter. 24 is 4 times 6, 4 being 2 times 2, 6 being 2 times 3. Cool, effort. 168, I don't know. 284? That works, right? But we divide that by 4. That'd be 4 and 21. 4 breaks down to 2 times 2, 21 into 2 times, or 3 times 7. $40, 10 times 4, 10 being 2 times 5, 4 being 2 times 2. Cool, effort. Now we just go through it and say, well, what's common to all of them? There's a 2 common to each one there. They all have at least one other 2, right? Any more? Yeah, okay. There's a 2, there's a 2, there's a 2. This one has a 3, this one has a 5, this one has a 3 and a 7. None of those are gonna work out, right? Even if these 2 have 3s, it would have to be common to each one. Or UCF would be 2 times 2 times 2, or 8. Like it? Do we hate it? Do we understand it? Do we not understand it? It gets messy when I don't have any feedback. Then I just go with my piece. Number 4 has better numbers. 196, 224, 462. Okay. General idea on something like this, you don't have a clue, but you know it's even. Slap a 2 on it, see what happens. 196, you gotta divide it by 2, you get 98. Oh, look, it's still even. Divide it by 2, you get 49, which is 7 times 7. Cool. I like it, right? 224, we might look at that and say, well, I bet that's divisible by at least a couple of 2s. Let's try a 4. 4 and 56, well, looks like we had one more 2 in there. 1 or 2, right? 56, we can divide that by 4 again. We get 14. 2, 7. Got kind of a horrible jumbled mess. So I'm gonna go ahead and cross out the things that I know I don't have to worry about anymore. Let's just do it for one. That'll make it a little easier to look at. 462. Well, if I chop every one of those digits in half, I get 231. And that's the only chopping in half it's gonna get. There's no more even numbers that'll go into that. 231, I might try a 3. 3 times 77, gee, I wonder what goes into that. 7 and 11. Okay. So you got them all broken down. Go through it, say what's common to each one. There's a 2, there's a 2, there's a 2. This one doesn't have any more 2s, so can't circle any more 2s. They do all have that 1 7 in common, right? We get 2 and a 7, 14. Do we like it? Do we hate it? Do you have any feedback? You guys awake? Anybody here? Number 5, without actually writing anything down, what is the greatest common factor? Yeah. Because it can be no bigger than the smallest number, right? If I have all of these different factors and then I have a 2 and I say, what's the greatest common factor across all of them? I can't pull something out of 2 that's larger than 2. They're all even, so 2, right? Oh, hey, a bunch of deer. Sorry, deer. Daycare's closed. So. It's a decent application. We look at the right side. I think we're only gonna do number 8 there. I'm just gonna cram it onto the side over here. But it says find the greatest common factor, simplify. We have 196 over 462. And the main reason I'm putting it off to the side is because, well, we just broke down 196 and 462, right? And we figured out that the largest thing they had in common, well, all 3 of these had in common, but it still happens to be the case with just these 2. But they had 14 in common, right? So one of the applications of this would be to divide the top and the bottom by 14. So you could say, oh yeah, 14 goes into 196. I don't know how many times, probably 2 times 7, 14 times. And 462 divided by 14. Well, once I get rid of the 2 and the 7 off of that 462, what factors do I have left? I have that 3 and the 11, right? That means this divided by that is going to give you 3 and the 11 left, or 33. So you could, if you're chopping off factors, you could just multiply the ones that you have left. Look at it that way. And that way you don't even need a calculator. You've already broken these down. That's a useful application of this. Now, go to something very similar, yet it usually makes people a lot angry. That's least common multiple. So these are set up exactly the same way, but greatest common factor was the largest number that could fit into all of your numbers. This is the other way around. It's the smallest number that all of your numbers could fit into. So think of it as you actually used it already when you're getting a common denominator with fractions. Think about it as common denominator. If I'm trying to get a common denominator between 2 fractions, I have to get them up to the same number, right? I can't chop them up. I can't make them smaller. They have to move upwards to the same number. That's exactly what you're doing here, is you're finding the smallest thing that all of them could fit into. Least common multiple. For each number, you break it down into its prime factors using a factor tree. Okay, check. We've done that a few times now. list all of the different prime factors you found, including each one the most times it appears in any of the numbers. So that's usually where I lose people. Then you multiply all of those prime factors together. So the general idea is that you're looking for something that is composed of all of the factors of all of your numbers. And you're just making sure you have the least amount of each of them necessary. So for instance, on this particular example, you have 12, 15, and 18. So you set up your factor trees, and then you look at each individual prime factor and look for the most amount of that factor that is available in any specific tree. So like 2, number 12 has 2 2s. There's none in 15, and there's 1 in 18. So you think, okay, the largest amount I just said was 2 of them, right, out of 12? So you have to have at least that many 2s to be able to fit the 12 into it. Okay, so we're going to take those 2 2s. We're going to say those are part of our least common multiple. Then you go to the next number, 3. There's 1 in 12, 1 in 15, and 2 in 18. Well, again, the most that any of them have is the 2 of them in 18. So we need those 2. So far we got 2 2s and 2 3s. Then the next factor is 5. The only one that's hanging out in that 15, right? So once you would have all of those together, the 2 times 2 times 3, 3 times 5, and the 2 times 3 times 3, all of those could fit into those specific factors that we just pulled out. Because if you look at the last bullet point there, it says multiply them all together. That's what we're saying our greatest common factor is. And you can actually look at that and say, well, do all the factors in 12 fit in there? Yeah, there's 2 2s and a 3, check. All the factors in 15 fit in there? A 3 and 5? Yeah, those are covered, check. And does 18 go into there? Is there a 2 and 2 3s? Yeah, it does, so check. So that's essentially, that makes you have the smallest thing that's going to be a multiple of all of those numbers. You could write down multiples of 12, multiples of 15, multiples of 18. And the first time they're all going to have the same number in common would be 180. Love this image because that is 100% something that we do. I absolutely have pushed an office chair over a mile because I didn't want to ask somebody for help. Man, those suckers make some noise going over sidewalks. I will tell you that. So a couple of these are bizarrely easy, right? If I had, for number 1, we have 4 and 5, least common multiple. Think about it as a fraction. If I had 1 over 4 plus 1 over 5, what would I have to get the denominator up to? 20, right? That's the first time that you would have 4 and 5 fitting into the same number. It's not going to be 10, it's not going to be 30, it's going to be 20. And that's the idea with least common multiple. That's one of the effective uses of it, is just in really ugly fractions. So for instance, let's actually do number 2, 14 and 21. So each of these we just make factor trees for. This one's 2 times 7, this one's 3 times 7. Not bad, right? The idea that I would look at this and say, okay, well, what's the most amount of, I'll start from the bottom and work my way. What's the most amount of 2s that any of these have? Just that one, right? None over here. So we need that 1, 2. What's the amount of 3s that either of them have? That one. And then what's the most amount of 7s any of them have? just one, right? Each of these has 1 7. So we're not trying to take all of the factors and put them together. We're trying to get something where if I looked at each one of these numbers, all of its factors would fit into this. 2 and 7, check. 3 and 7, check. Okay. So all we got to do, multiply them together, you end up with 6 times 7, 42. Do it make sense? Number 3, we have 24, 11, and 14. So 24, we've done this one before. You can break it down however you want to. I'm personally going to do 4 times 6 and break each of those down separately. 11 is prime. Can't do anything with that, right? And then 14, 2 times 7. So not bad, right? So in order to find the least common multiple, again, start from the lowest factor, work your way up. Most amount of 2's that any of them has. This one has 3, this one has 1. Probably the 3, right? We take those 3 2's, part of our LCM. Next factor up would be 3. Only one of those hanging out, so I need that. Next factor up would be 7. And believe it or not, yes, we do need that 11. We need to make sure that whatever number this is a multiple of 11. So we have to throw that in there as well. So at this point, you're just going to multiply all those guys together. We could be cheap about it. These 4 were everything in 24, so we'd start with 24 times 11 and times 7. So I get 1,848. Which I could look at that and say, you know, I don't think I could look at that and think that is very clearly divisible by 11. Why am I saying that? Well, because if you had to find the smallest multiple of all of those that they have in common, it is going to take you a very long time, right? Imagine writing out the multiples of 11 until you hit 1,848. That would suck, right? And then you'd have to do the same for 24, the same for 14. And keep going until they have something in common. I wouldn't want to do that. And neither would you. That's why we have this. Are we understanding it or are we confused? No? 5, 20, 24, and 12. Break each of these down, right? 20, that's going to be 2 times 10, and being 2 times 5. 24, gee, I wonder. Done this one enough times today. 12, 6, which is 2 times 3. So if I'm looking for my LCM, I got a lot of options, right? Lots of 2s, lots of 3s. Well, not so many 3s, but so. So the amount of 2s we have, there's 2 in this one. There's 3 in this one. And there's 2 in that one. Most amount I just said, 3 of them. Cool. Next number up, we have 3. There's 1 here, there's 1 here. We only need 1. Okay, and the next number up, 5. Slap that 5 on there. There we go. So we have 3 2s, a 3, and a 5. Multiply them all together, we get 120. What do we think? Makes sense. Doable? That's good because this is usually the ugliest thing to cover. I have had students break down crying over this, actually. 100% have. The other thing I can remember people breaking down and crying over was composite functions. Which, to be fair, at this level, might actually make you guys break down and cry too. No, I want a video. Like that. Yeah, so those are fun. F of x equals g of x equals, and you have to find f of g, g of f. We're putting an entire function into another one. Those are fun. All right, so I covered a lot of ground and I'm tired. So I think we're gonna call it good there. All right, I think we're happy to, stop.